Now, the topic is kurtosis. We studied about different methods of central tendency, mean, median, mode, geometric mean, harmonic mean. We talked about measures of dispersion, maybe the range, mean deviation, standard deviation, quartile deviation. Why we studied these measures, both of central tendency as well as dispersion, to understand the given data distribution of the data. Another tool was given to you, that is skewness, where we can see that how the distribution is distributed as with reference to the normal distribution. Even after so many tools which we have in our hand, still there is a need of one more method which explains the distribution, the type of distribution, the characteristics of distribution. Like skewness, kurtosis is also in one of the statistical measure which is used to describe the distribution. It describes how much of the probability distribution that falls in the tails versus its center. Tails, that is the two extreme of the curve, center, the central part where the peak comes. As we know that as far as the concept of kurtosis is concerned, Carl Pearson has studied it deeply. He called it convexity of the curve. The concept of convex and concave that we studied in the case of lens and mirrors in physics. Convex, that is the hump, the extended part at the center, and which is thinner at the ends. So more the convex is the curve, the kurtosis is said to be positive. We'll study. The less the convexity, kurtosis is accordingly can be calculated. So the degree of the kurtosis of any distribution, how it can be measured, is measured relative to that of normal curve. What happens in normal curve? As far as skewness is concerned, normal distribution is in central clustering is at the center, and both the ends of the normal distribution are exactly symmetrical to the other end. But what happens in kurtosis? If the curve is steeper as compared to the normal curve, it will be called laptokurtic. If the curve is flatter than the normal curve, it will be called platykurtic. And if it is exactly similar to the normal curve where the height or the peak of the curve doesn't rises or nor it is flattened, then it is called mesokurtic. As we can see in the figure, we can see that the peakness is higher, or it is equal to the normal curve, or it is less. So I can say the kurtosis, it is a statistical measure which is used to describe the degree to which the data is clustered at the center and in the tails. Now, if I say in many books and in many statisticians, the kurtosis is described with reference to the peak, but majority they talk about tail, how the tail is coming out of the distribution, whether it is thick, whether it is thin. We can say the tail itself is thick and thin when the peak of the curve increases or decreases, as it happens in the laptokurtic and platykurtic. In normal distribution curve, when we calculate, when algebraic mathematically, if we measure the using certain formula, what we get in normal curve, the value comes equal to 3. We'll take care how it comes 3, what the formula has been applied. But just for understanding, if I say in normal distribution, let's say, as you can see in the figure, it is there that if this is the normal curve. If I say in this normal curve, the kurtosis I calculate and it is found 3.0. There are some standards which we have to take care. From where it comes, that is another chapter to be taken care. But if the distribution which you are studying is like this, as it is seen here, I would say this is a laptokurtic curve. When it is a laptokurtic curve, in that case, your kurtosis will come more than 3.0. when some calculation will be done, some formula will be applied, the value if comes more than 3.0, how it is interpreted, we would say that your distribution which you are studying, that is more towards higher in the center, and its ends are thinner, but it never touches the x-axis like this. And how is the peak? Peak is going higher than the normal curve. Look. So in this case, when calculation is done, it comes more than 3.0. If graph is seen, in graph, it looks like this. What happens in the case of plateautic then? Let's see, this is plateautic. This is plateautic. What happens with this type of? This is plateautic. In that case, graphical representation is that the peak is, look, from the normal distribution, peak is lower side. What happens towards tail? Tail is see thicker. दोनों ends जो होते हैं tails की वो थोड़े thick होंगे, heavy कहते हैं. डेटा यहाँ बहुत सारा है, सेंट्रल में डेटा कम हो गया. इस केस में कर्टोसिस जब आप कैलकुलेट करेंगे यूजिंग द फॉर्मूला, it will come less than 3.0. The value will come less than. Why 3.0? I said it can be taken care in some under some other topic. But this is a reference. If it comes more than 3, we call it lactokurtic. If it is less than 3, we call it plateaukurtic. What happens when it comes equal to 3? Yes, when it comes equal to 3, it has been said mesokurtic. So in mesokurtic, the kurtosis will come equal to 3.0. Other way around, if I say, in case if I find the difference between the kurtosis of your distribution and the normal distribution, in that case, this kurtosis has to be positive, this is negative, and this is 0. What I said? Let's see. Kurtosis which you have calculated is 3.2. Now either you can say 3.2 is greater than 3, lactokurtic. In many books, you may find 3.2 minus 3, which is coming positive 0.2. So they say if the difference comes positive, it's called lactokurtic. Either way, it's one and the same thing. So we should not get confused with two different ways of understanding any concept. So lactokurtic, plateaukurtic, and mesokurtic are these three concepts which talks about distribution. Now let us connect it with some example. For example, if I ask you, there are basically kurtosis is more applied in financial analysis where the risk has to be taken care. But for a simple example, if I say, for example, there is a class where I have seen that the performance of majority of the students is somewhere 80%. What happens in lactokurtic? In lactokurtic, majority of the students, they are performing, look, between 70 to 90. Let's see this. And there are very few students who are performing less than 70, very few students who are very intelligent performing more than 90. What type of data I would say? I would say this class is comprised of the students which are of same intellectual level, same attitude, same performance. Here, whenever generally what happens in coaching is the top batch, like the top batch, the distribution will be like this. They will work on this data. All of them are of same intellectual level, same intelligence. Now, if the distribution comes like this, what does it mean? These are extreme values. Look, these are extreme values. So we can find the data in these extreme values also. This is rare or extreme values. So here the class is of varied performance. You have students in the lower performance who has lower scores. You have the students who are performing good. You have the students which are performing average. So you have all the different students of different intelligence. In this way, we can understand what happens when the distribution is plotted in the form of kurtosis. What is excess kurtosis then? Excess kurtosis always talks about lacto or plateau. It is more than 3 or it is less than 3, means as the kurtosis goes away from 3, kurtosis will be called excess. How much excess the kurtosis is? How far it is going out of 3? This is minus 3.0. This is plus 3.0. This is certain that the standard 3 times standard deviation taken care by 99% will take care in future for the step chapters. But for right now, for understanding, if I say this values and this values, these are extreme values. These are extreme values, right? More it goes away from 3, more it goes away from 3, more excessivity the kurtosis does have. Many times instead of lacto and plateau, we can call it positive and negative also. So simply positive means lacto. If it is more than 3, we can call it positive kurtosis. It is less than 3, we call it negative kurtosis. Normal distribution always take care that in normal distribution, as we know, mean, median, mode are always same. Besides that, in normal distribution, one important thing always remains is that even on the kurtosis, when you do, whether you get plateau, you get plateau, meso, everywhere always take care that these two ends, they never touches this x-axis. They never touches this x-axis. So this is called, this spelling is right, asymptotic tail. This is symptotic characteristic, I would say. This is one of the characteristic of a normal distribution where the curves doesn't touch to the x-axis. Both of them are symmetrical. The left side and right side are symmetrical. That is, we are talking about the normal distribution. Now, if I ask you to find out the kurtosis, this value which we're talking about, if your value comes greater than 3, if your value comes less than 3, if it comes 3, how this value is calculated? So there is a mathematical formula. We apply that mathematical formula on this, and then we calculate how the kurtosis is calculated and then compared with 3, and then result is obtained whether we have positive or negative or 0 kurtosis. Now let us calculate the value of kurtosis algebraically with an example. We have this individual series. The data is given here as 73, 70, 71, 73, and so on. First, let us write down the formula for kurtosis. How to calculate it? You have to find out, you may call it the fourth moment. Fourth. How to find the fourth moment? It is summation of x minus x mean to the power 4 divided by number of observation into standard deviation. What is x minus x mean? X mean means mean of the given data. When you find out the difference, what we call d, generally we represent it by d to the power 4 we have to calculate. And then you have to sum it. As this in the example, you can see we have calculated mean. The mean which we have calculated over here is coming 71. You see, if you add all these values, sum of all, this is the formula, sum of all the values divided by n. Repeatedly we do this work. Summation of all the values, sum here comes 710. Number of observation, how many are there? 10. So I get mean is equal to 71, right? Look at here. We got it. What I'm supposed to do is, when you get these value x, find out x minus x mean. X minus x mean means all the x values minus 71. So what are the values which I'm getting is 2, minus 1, 0. See, values of x are 71, 70, 71, so on. So this is x minus x mean. I'm getting 2, minus 1, 0, 2, minus 3, 4. This is the process and it goes. You find out the sum of x minus x mean, right? It will come 0. Second, after this, you have to square it. Up to what we have to go? Look at it in the formula, up to the power 4. So we will square it. This square will be required in standard deviation formula. What is the standard deviation? How you used to calculate standard deviation in the case of individual series? That is sum of x minus x mean to the power 2 divided by n, total number of observations. Remember the formula of standard deviation. This is in the case of individual series. Talking about individual series when we do not have frequency. So using this formula of standard deviation where this column will be used, I will calculate the square of this d which you used to call 4, 1, 0, 4, 3, 3 is 9, 4, 4 is 16. Goes. See, it's complete. You can see the complete column values will come. Find out the sum of this column x minus x bar to whole power square, sum of this column. It is coming 64. One more thing which I require from this table is this numerator. So what I'll do, this is the d. What I will going to do is to the power 4. Put this d to the power 4. 2 to the power 4, right? 2 into 2 into 2 into 2. So we get 16, right? Same to the power 4 minus 1. Minus, remember when there is minus sign, if it is an even number like 2, like 4, it always give you positive. Basic mathematics, school level mathematics. If minus is there and if you multiply to the power even numbers like 3, 5, always gives you negative. Just refresh that. Never make mistake with the signs. Minus 1 to the power 4, it gives you again 1. 0 to the power, anything gives you 0. 2 to the power 4 gives you 16. 3 to the power 4, it gives you 81, and the column goes like that. Find out the sum of this column, sum of this column, because this will be used in numerator of the while calculating the kurtosis. How much it is coming? It will come 1012. Do this exercise, check it whether it comes 1012. This column, the last column summation of x minus x bar to the power 4 and the summation of this column. This will be used in your kurtosis formula. Look at here. This is my kurtosis formula. I'm going to put it over here and will calculate kurtosis. So either I can place directly or either can calculate standard deviation first. So let me calculate, put this value 64 divided by n. How many observations are there? There are 10 observations. So I get under root 6.4. So what is the standard deviation? It will come 2.5298. Right? 2.5298. This is standard deviation, and this standard deviation I can use it directly here. It is yes. One more thing. It is this I missed to the power. This value will be used here. This summation will be used here, and I will calculate the kurtosis. So the kurtosis for the given data comes out summation of this 1012 divided by n. N means total number of observations. They are 10. 10 number of observations. Multiply by standard deviation to the power 4. Because simple calculator, if you can use, you can go use, calculate this value. When you calculate this value, it comes somewhere 2.4707. What is this? This is kurtosis. Kurtosis of what? This given data. Now, related, just recall what we started. If the kurtosis of the given data comes less than 3, what I will call it? Negative kurtosis or plateaukurtic. Yeah. So I would say plateaukurtic. Plateaukurtic means it is tails are heavy. More observations are there in the tails. Peak is flatter. It is more flat curve. So it's called plateaukurtic. In this case, I can say that my data, if I have to represent, I can say my data is as compared to the normal curve, my data is flat. More towards extreme value. Observations are there more towards extreme values. How much is the value? 2.4707 is the value, and the inference interpretation is the distribution is flatter, is away. 2.5 means somewhere around 0.5, somewhere around 0.40 something, it is away from the normal distribution. So it is a plateautic case. Now we'll calculate kurtosis in the case of the data when it is given in the form of discrete series. Individual series we covered. Now in the case of discrete series, what happens in the case of discrete series? The values are given and frequencies are given in that case. Same way, remember the formula for the kurtosis as we did it? The kurtosis we can calculate using the formula. This is called fourth moment, x minus x to the power 4 divided by n into standard deviation to the power 4. You can see this formula require the step 1 is mean. And in the case of discrete series, we have to calculate mean as we studied earlier with this formula that we can multiply frequency with the value. We sum this value and then whatever the values come, we put it in the formula. Sum of fx divided by n. N is sum of frequency. Using this concept, I have calculated the mean in the given data. You see, the values of x are given, the frequency are given, multiplication of these two gives you the third column, that is fx, and you add these values, you are getting 55. When I get 55, I put it in the formula where I get this 55 divided by number of observation. Number of observation is, do not calculate that there are 5 observations. No. Add these values. Number of observation is always summation of frequency. So it is coming 25. So what is the mean? Mean is 2.2. What I am supposed to do is, I need x minus x mean to the power 4.1. I also need to calculate standard deviation. To calculate standard deviation, remember the formula of standard deviation is under root. What in that in the case of discrete series? So in the case of discrete series, it is f, you call it d, or you can say x minus x bar whole square divided by n, what is summation of frequency. This is the formula for the standard deviation in the case of discrete series when the data is given in the form of value and frequency. So what I need, two important things. X minus x bar to the power 4 required, x minus x bar to the power 2 required. So we'll do in one single table. We'll perform x minus x bar, we call it, you can call it t, to single value. What we do? We square it, this value, this column values, you are square it, and the last we put to the power 4. To the power 4. The sum of these two columns, these two values will be placed in this formula. So if I find the d values, you can calculate, should try to calculate the d values, it will come minus 2.2, then it is coming minus 1.2, 0.2, 0.8, 1.8. From where it came? These are the x values, 0, 1, 2, 3, 4. So 0 minus 2.2, right? 1 minus 2.2, look, 1.2. 2 minus 2.2, 3 minus 2.2, and 4 minus 2.2, correct? Square these values, you will get 4.84. Square this value, you get 1.4, I guess 1.2. You square it, somewhere, it's 112, 1.44, should be 1.4, right? If you square this come 0.04, you square it, 0.64, and you square this value. As we did at kurtosis in the case of individual series, We have covered in the case of discrete series. Now, if the data is given in the form of class interval, that we call it group data, in that case, the formula of the kurtosis will remain same as it was there in the case of discrete series. Remember, the kurtosis is, the formula for the kurtosis is summation frequency x minus x mean to the power 4 n multiplied by standard deviation to the power 4. Same formula we'll be using. Have an example on the screen. See, class intervals are given. Find out the midpoint. Remember the formula of finding the mean in the case of class interval in group data. The group data mean is calculated using the, if I say midpoint, I represent the midpoint with the m, you find the value from the mean using this formula, right? If I use this formula, I can calculate the mean in this case, in this given data. What is it coming? The summation of frequency FM. See, it is, the values are 52 divided. What summation, number of observation? It is frequency. Add the summation of frequency. It comes 5.2. Same, try to find out the deviation from the mean, that square it, which will be used in standard deviation formula, to the power 4, it will be used in numerical. What is the standard deviation for the formula for this individual series? Under root summation frequency d square divided by summation f. Look this, these are the two formula which will be used in this kurtosis. So what I'm supposed to do, I have to find out the deviation from the values, which I can call it d or x minus x bar. So this column comes. Square it and multiply it with frequency. So what I get? I get this frequency x minus x bar to the power square. Summation of this value. This addition of this column will give you this frequency into x minus x bar to the power square. It comes 35.6. Where it will be used? It will be used in this formulas of standard deviation. Put this value in the standard deviation as a numerator, summation of the frequency as a denominator, which is 10. Calculate standard deviation. So I put this value under root 35.6 divided by 10. So this value is coming 1.88. This standard deviation value will be used in the formula here and this numerator. That is the summation of the last column in this table. See on the screen, the summation of the last column is 299.792. Use this value in the numerator, use this value in the denominator. You will calculate kurtosis. It comes somewhere. It is coming 2.36, right? Important part is, besides the calculation, never ever make mistakes with the calculation and multiplication. Besides calculation and getting this 2.36, very important part is to find and interpret whether it is plateautic, lactocotic, or mesocotic. As it was in the earlier example, it is less than 3. So it is we would say, because it is less than 3, it is plateautic distribution. So kurtosis we have talked about. We talked about skewness. Skewness where the distribution was, how far the distribution is. I mean, distribution has been shifted right side or left side as compared to the normal curve. So that talked about skewness. What kurtosis talking about? Kurtosis बात करता है कि distribution का concentration central value की तरफ है या spread है. Means clustering is more towards the central value or towards tails. So I would say kurtosis describes the fatness of the tails which is found in the probability distribution table. When I say flatness of the tail, how much data is there in the tails? If it is more, the tail will be more fat. If the distribution observations are less towards tail, it is said to be thin tail. As far as application is applied, this application is more in the higher studies when we go for testing of hypothesis, rejection and the acceptance of hypothesis. In higher chapters, in the next, maybe in the last 4th or 5th chapter, application use of this concept will be there. Besides that, we have talked about what is the kurtosis in the case of normal distribution. It is 3. How it comes 3, as I said, we'll taken care of again from where this 3 value comes. But right now, 3.0 is the kurtosis found in the normal distribution. Then one more important point which we have talked about, application, as I said. Besides that, in financial analysis also this kurtosis is used to find out the risk, how much the risk is there in particular investment or some policy.